session. The second speaker is Bangxin Wang from Hamburg, and he will tell us about. Excuse me. Sorry. He'll tell us about high-cross table categories and applications.
Thanks for organizing such a great event and also for the opportunity to speak here. So this is going to be a algebraic talk, but before doing that, I want to start with some topological information. As it has already been introduced in various talks, we have this DGGPR construction for non-semisimple 3D TQFT, and for simplicity, I'll just talk about invariants. So basically, starting from a ribbon category, by doing this DGGPR construction, you get invariant of such pair. So where this M is a three-manifold and this T is an embedded ring or ribbon graph. And then one can ask whether we can add some cohomological data so that here we get invariant of such a people where this omega is some first cohomologicals in M, removing the tubular neighborhood of T and take the coefficient group, some abelian group G. And the answer is yes. So there is a TQFT construction introduced by Tribe and Universität, and starting from a G-cross ribbon category. And why do I care about such invariants for such a triplet? Because there is a very well-known non-semisimple construction of 3D invariants by CGP. So it starts with a.
Or CGPs, not everybody knows the problem.
Yeah, I will write it down. So basically, starting from a they call it G relative.
DGGPR. Huh? That's what DGGPR.
GGPR, yeah.
GGPR is several people's name. It's Marco. This is Azad, and another G is Nathan Geer. P is Bertrand Tour. Okay. Tour and R is Ingo. Runkel. And so they call it G relative ribbon category. And there is a construction there. And the problem is that this construction is very different from this one. So basically, if you take a trivial group G, this construction just doesn't work. So it doesn't make sense to ask whether we can restrict to the trivial G case and just reprovide the GGPR construction. So what we want to do is to find a relation between this construction and this construction. But this construction, if we restrict to the degree 0, it will provide the GGPR. And what we can do is that from any G relative ribbon category, so basically this is a G graded ribbon category with some extra structures. So from any such category, we produce a G-cross ribbon category, and we run the TQFT construction. So they produce the same invariants. And then if we restrict G to be trivial, we get DGGPR. That's an ongoing project with GGPR. So for this talk, I want to mainly focus here, and especially from a very concrete example here, we want to produce a G-cross-ribbon category. And along this way, we generalize this G-cross-ribbon category a little bit. So this is what I'm going to tell you in this talk. This talk is going to be about high-cross. Okay, so ribbon structure is not so illuminating. I will just make it simple and just talk about high-cross braided category. And where chi is the cross module. This is joint work with Azad and let me first remind you what a cross module is. A cross module is such a tuple GH gamma where GH are groups, not necessarily abelian, and we have a good homomorphism pi from G to H, and we have a H action on G. Such that the following two conditions hold. So the first is so this is this H with right triangle is my notation for gamma H. So you evaluate kind of H acting on G is H and H inverse. And second, we have time G acting on G prime, we just get G prime the inverse. Okay, and then a category C is called degraded additive. If we can write it as such direct sum of a family of categories. So by writing like this, I implicitly mean if you take objects living in to different degrees, there is no morphism between them. And this is called G-graded monoidal. So this is going to be a list of definitions. Each row below is the thing above with some more structure. So a G-graded monoidal category is a G-graded additive category together with a the tensor product. And it should satisfy so the tensor product should respect the degree. So this may be not the best notation, but I guess you see what I mean. And it's G-graded monoidal with H action. And you see here. Okay, I don't know. If we have a strict monoidal functor, a phi from H to automorphism, tensor automorphism of C. such that each group element will be sent to a functor, and the functor I have denoted like this. This value H acting on G. So in my talk, I will assume this another functor to be stripped. Finally, it is called chi-cross braiding. If we take any two objects, X in CG, Y in CK, we have an isomorphism from X tensor Y to Y chi of G tensor X. Satisfying some naturality conditions and Young-Buck's equation. And furthermore, we want this H acting is somehow the braiding monoidal. So which means we have the following diagram. So we have C, just this isomorphic C. I can apply the functor to it and consider its image. Then it is going to be and because H is a monoidal functor, I have coherence data. And there are also the same here. And here I want to use a cross gradient for H, X, and H. And we should this diagram should commute. And there are 2 points that we have to be careful. But here, X tensor Y as the object is in C GK, and this object here living in what's that? This is chi G acting on K times G. But as I have already told you here, if they are in different degrees, there can be no morphism between them, which means we must have GK G inverse equals to chi of G acting on K, which is exactly this condition here, right? And also here we have to check the target object for this isomorphism is actually I of H acting on G times Y acting on times H acting on Y tensor HX. So these two objects should coincide, which means these two group elements should be the same. And this is actually just kind of H acting on G equals to H chi G H inverse, which is the first condition here. So to make sense of a cross braiding, we really need GH chi and this gamma to form a cross multiply. So let me give a remark. So if you take a if you take the identity from G to G and you consider G acting on itself by conjugation, this is a cross module. So you can consider this crossed braided category. This is just a G cross braided category. In the more usual sense. And another remark is that a high cross braided category is always image of high cross braided. So we can indeed recover the more usual definition. And then I want to tell you two constructions of such categories. So how can we build one such category? The first one is a Hopf algebraic construction. So basically, we're asking whether we can define some kind of Hopf algebra. The representation category is exactly a high cross braided category. This is like the usual Tanakian reconstruction thing. Right? So from a tensor category, you want to find a Hopf algebra. Because you have coproduct, and on the representation category, you have a tensor product. It's basically the same idea. The definition, a high cross.
Can you give maybe just simple, semi-simple example, or just something?
A semi-simple example of a what?
I don't know, something based on fusion categories, or like
Of what?
without going of G crossed or chi crossed.
I've never thought about this question. Easy, but we are going to provide a non-semi-simple example.
I know, yes.
Okay. Yeah. Okay. Let me just continue. A high cross braided cloth algebra. Is a family of unital associative algebras together with many structures. So it has a family of co-multiplications which goes from UAB to UA tensor U. And it had a co-unit from the neutral component to the ground field state. And you have a family of antipodes. It goes from ULA to the inverse. And a family of algebra isomorphism. Goes from UA to UHFT now. H and H, and they have a family of invertible objects, invertible elements. omega A, B, A in U H acting on A tensor in U H acting on B. And finally, we have a family of R matrices. Okay, so the point is that the representation category of this U is backwards graded. Basically, the cohomological gives you a graded monoidal structure. This gives you the tensor unit. This gives you rigidity. It gives you H action on the representation category by you just pick the same underlying a module, but twist the algebra action by this algebra isomorphism. And this inversible element omega gives you this coherence data for H action. And finally, this gives you the Patureau spring. And so this part is not very interesting and illuminating, so I just list these conditions. And what we have done is that we use the second approach, which I'm just about to tell you. We constructed a Patureau ribbon category, and then we run this this Canadian reconstruction procedure, and we get a Patureau ribbon of algebra. So we have explicit cohomologications and blah blah blah. Yeah. So now I'm going to tell you the second approach from twisted local modules. Let's start with C being a monoidal SL Dillian category, and we take a algebra object inside C. So instead of giving definitions, I will try to draw many pictures, which means I draw a diagram from bottom to top. So this is multiplication, and it should be unital and associative, which means I have such a morphism, and I want associativity. Yeah. All these diagrams are in C. And what is an A module in C? It's an object in C. A module M in C. So we draw diagrams. We have a morphism from A tensor M to M itself. Again, this is diagram in C, and we have this. Okay, so I guess these are pretty well known, and now we will take two leaps of A in the dream field center of C, which means let's get A bar and A tilde in the center of C, such that so we have this forgetful functor from center to C, and I want it sends both A and A tilde to A. And so I will also draw a picture for this. Not very easy to manage.
I know, right? It's a workout.
Okay, so what does it mean for something living in the center of C? It means so A bar is basically the underlying object A together with a half braiding, and I will draw it like this. Let's say orange dot here, and anything on X is natural. You can move morphisms on this strand. I say this is A, and the same for A bar. Put a green dot here. So sorry for A tilde. And being a commutative algebra means you can first do such a half gradient for A itself, and you do a multiplication. So here I put a orange dot here. It means A bar is a commutative algebra. I also want, if I put a green dot here, it should also be the same as this. Okay, and then now we can define a monoidal structure on the category of A modules in C. This is monoidal. So we define M, tensor N, so it is a co-kernel of again diagram with C. Right. Use A bar to define the monoidal structure, not using A tilde. And equivalently, this is the same as saying this is the co-equalizer of the following thing. So if you are not in the abelian setting, you can still do this. And this morphism is this, and this morphism is this. Okay. And now let's consider a G action Ra. And I want it to be a algebra automorphism, which means for any G, I can first do this, and it should be the same as first multiplication and then act. And also, I want them to be when you lift this each by G to the derivative center, it should be a multiple there. And more precisely, I want to be able to do this. Should be the same as first. Yeah, the point is that I want to, so by definition of derivative center, I only have naturality on this strand. So I want this to also be natural on this A strand. And I want to be able to do this for both half braidings. Okay, now I can make our main definition. Definition. And A module the M is called G local. So actually, with respect to my choices of A bar, tilde, and this prime. If so I put A here, I put M here. I put this orange dot here. This means this is the inverse of this half braiding. So if you compose this half braiding and this together, you can see you can do this randomized too. But the point is A is always above, which is the inverse of that. It should equal to we have by G and like this. And put my green dot here. So again, this is the inverse of this half braiding. Remark. For those who are familiar with local modules, you may ask why we define this funny notion. The point is this is really a generalization of that. I'll tell you how we can first remark. First remark is A as regular A module is E local. E local means here is just identity, and because both algebra I assume them to be commutative, so they are both equal to just doing the multiplication. So A is regular A module is always E local. And second, as I said, I want to recover the notion of standard local module. And how? So we assume C itself is already braided. And I will take I'll take my first choice to just be the braiding effect category. And I will choose my green half braiding will be with this this is the inverse of XA, CXA in the braided category. If I take this choice and I take G to be E, this recovers the usual notion of local module. Okay, the position. I can consider the category of all G local modules. This is G local modules. And this is gradient monoidal. Let me maybe show you one proof so you see how this works. Let's try to prove this. What we have to show is basically if we take a G local module and if we and another N, which is K local, we want M as N to be GK local. How to do this? Maybe I have already it's here. This is again a diagram in C. This is the morphism, also morphism in C. I can do this. And since by naturality I can move this below, which means this is by the definition I can do this. And then I can again this is a co-equalizer. I can do this. And then here you can do a randomizer 2. And remove all this. And just act here. And then here I can use my definition of G-locality, which means I can change this orange dot to a green one with the cost here adding a 5K. And then I can do the randomizer 2 again. And then go here. Oh, then it's not a randomizer, it's just by the definition of this co-equalizer. I do it again, and here again I can apply my definition of G-locality, and I change this orange dot by a green one by the cost of inserting a 5G here, but I assume 5G, I can always move 5G along my strand, so I have 5G. And then again, by naturality, I can move the whole diagram, move these 2 green dots here. And since this is a co-equalizer, it's always epimorphism, I can just ignore this part of that. That one. Okay, so now we have given this graded A module is a G-graded monoidal structure. The next step is to define a H action on this category. So we need another group H. H another group. And I will need a H action on G, and I will need a H action on A. So again, this H action on A should satisfy this 2 properties. I want these 2 actions to be compatible in the following sense. So this diagram should come in. Phi is my G action there. And here I can apply mu and phi. So like that. Alt A. And here I just write tabulation. This diagram that should be commutative. And by giving such a H action on A, I can actually define a H action on module by the following way. So again, diagram in C.
I don't think people see it from there.
Okay, let's go ahead and move to the other side.
Not really much better here. I mean, it's
Okay.
so you can just focus more on ideas. So.
Okay. Let me finish this. So you define H action like this, then this category becomes a G-graded molecular category with an H action, and then we want to define a chi-cross braiding on it. Then you just assume more conditions, and yeah, there's a way to do that, and the proof follows more like the same way as just manipulate things, moving things around. I don't have time to do this before, and something here. And I want to tell you, so okay, at the end, we can show with some extra structure. This is a chi-cross braiding category, and we provide an explicit example. So if you take your C to be the weight modules of on-road UQSL2. Weight modules means the H action and also therefore the K action on this module should be diagonalizable. And we take an algebra A to be the Z family of one-dimensional representations. This means H acts by 2pk. Sorry, here I choose Q to be 2p roots of unity. So this C is a Runkel category. So now I want to define my set my orange half braiding to be just a braiding. And I want to use my green half braiding to be the permutation. And my phi, I choose a group G to be a C mod 2C to automorphism of H. Basically, for each G in C mod 2C, phi G goes H to A. We take this as a generating vector in this vector space. Is ascended to E, BKG, and yeah, just by a constant. And I define my group H is C mod C. It also goes to A. So for any H in C mod Z, it sends 1 to BK to e to the power minus Q P A H. And then okay, there's yet another choice of G C mod Z actions on A, but since I didn't introduce it. Okay, what I want to say is with such choices, consider this category. This is chi-cross driven tensor category. And it's finite in each degree, but since we have a C mod 2Z family of them, what is chi here? Okay, what is chi? Is a chi is
people don't see what you're writing, I think. So people from the back, they don't see what I mean. I see what you're writing, but
okay.
Right below, I think it's not seen.
G is C mod 2Z. G is C mod 2Z. H is C mod Z. And chi is the projection. So like x and x plus 1 sending to the same group element here. Okay, finally the result is you take this choice and consider A modules in C. This is a chi-cross driven category and finite in each degree. And by this reconstruction, theorem, we explicitly reconstruct the chi cross ribbon Hopf algebra, and we have explicit formula for coproducts, asymptotes, blah blah blah. Okay, I think I will just stop here.
Okay, thank you. There are questions? Robert?
Some very trivial questions, hopefully. But if you take two different lifts like you do of A and A bar of some algebra to the Runkel center, the way you can set a group G to be trivial. And then you look at local modules, and the C local modules identify the two actions, and this is monoidal. What is it plane?
You mean the monoidal structure?
Does it have a plane?
So I think, for instance, at least in our example, if you choose this hybrid to be this, and this to be just this permutation, they give you a different monoidal structure on this A module category, right? So at least I didn't. I think they are not even monoidal equivalent. So yeah, if that answers your question. So I think they are not. They are.
You were asking for more G trivial, right?
Just asking for G trivial, and to me that seems like you have some sort of identification.
For G trivial, you can restrict to like local modules here, but still it's different monoidal structure. They give different monoidal structure.
All modules has different monoidal structure, but for the local ones, do they happen to coincide? It's still different. Maybe we can discuss later.
Yeah.
And are the categories the same? Are the categories the same? Or categories of local modules for these two lifts?
I think, yeah, the point is just the monoidal structure here. Yes, you can use the orange one to define monoidal structure or the green one to define.
So to define what is local, you need two algebras.
Yes.
But for monoidal structure, you can choose.
Yes, that's right.
Right. So we need like
yes, throughout my talk, I actually okay, the role of these two algebras are not quite symmetric because I explicitly choose one to define monoidal structure. And then you ask me if it's the same as you use the other one, right? If we only consider local modules.
Yes, if the local modules should be A modules for which somehow these two tensor products happen to be the same.
Yeah. My impression was no. So, but maybe I made some mistakes somewhere. Yeah, maybe we can discuss. Yeah.
other questions, Juliana?
So could you quickly sum up how this K-cross machinery helps you address the initial topological problem?
Yeah. Okay. So this is a chi cross ribbon category. It's always like image of chi cross category. So here for this example, if you take chi to be single 2Z to single Z, it's always a single Z cross ribbon category. So you will always get something G crossed. But for instance, if you want to do computation for our explicit example, it's much easier to write it down in this setting instead of in the G cross setting. And for your question, whether there is some topological applications itself, I don't really know, but there is a related work by Biolizia and Switzer that defines the notion of chi-gradient monoidal category. So and this chi is related. So chi, you can take the classifying space of it. And so whose pi y is co-kernel of chi and pi q is kernel of chi. You can, and then you can define invariants for homotopy class of maps from M to that classifying space. But I think our notion will not do the same.
But the question was, how can you define now with this example, for example, any kind of TQFT?
Then we have to restrict it to the CMOS. That's it. Yeah, if that's your question, then yes. Okay, from this we can This is, if you group two gradients together, if you group this gradient x and x plus 1 together, it gives you a seamless equals kind of the g cross 1. You can run the HQFT construction immediately. And if you ask whether itself has can do something more than just g cross category, I don't know.
Okay, so you recover the known constructions with a bit more data that helps you make the
It's
computation.
immediate, just immediate. You group two degrees together. So if you have a G grading and you have a group homomorphism from G to another group, you automatically have a from G to H, you automatically have H grading, right? Yeah, it's immediate.
Okay, other questions? Seems not the case.